Good afternoon. My name is Dmitry Reinhold, and I'm a part of Team A02, and our project is design of digital cancer spheroid. Our team members are Allison, Vedant Patel, Nimit Patel, and me, Dmitry Reinhold. Our advisors are Dr. Gligorijevic and Dr. Tuzel, and coordinators Dr. Har-el. Our project is about growing a digital cancer spheroid in a lab and making 2D model out of that. The project explored how computational modeling can be applied to the field of spheroid-based cancer research. Cancer spheroids are in vitro three-dimensional cell models that mimic in vivo tumor growth by allowing for more accurate cell-cell and cell-to-matrix interactions. Our team took the approach of modeling cancer spheroid using an agent-based cellular parts model in a software called CompuCell 3D. Such a model aims to decrease the number of spheroids made in an experiment by allowing users to model spheroids in a way that they can easily manipulate different initial conditions to see how they affect the growth and invasive properties. Without having to grow the physical spheroids, data was extracted from images taken with a confocal microscope of a lab growth spheroids ranging from 90 to 3,000 cells. The model today is a simulated blob of cells that can proliferate and grow invasive strands. For the problem statement, figure out that cancer spheroids are more accurate in vitro cell model than 2D cell assays, but they're not used as often for the following reasons. First, they're costly to produce due to use of expensive materials such as collagen, and they take a long time to grow, up to 2 weeks in a lab, so the data will be a little bit out of date when we need that. For the design approach, we start by growing spheroids in the lab and process them with image analysis tools such as ImageJ. Then we extract data from the images and put that data into CompuCell 3D model environment where we created our model. Here in the pictures in red, we can see that it's 41 cell line type, and spheroids is immersed in extracellular matrix, which is collagen, and number of cells is different from each spheroid, from 19, 187, 375, 750, 1500, and 3000. And we use Fuki fluorescent dye to color them so we can do the image analysis in that. For the image analysis part, the parameters that we measured were spheroid core area, total spheroid area, invasive strand length, invasive strand width, number of invasive strands, and cell counting. For the software and the test results, we have a couple slides here showing the model of that with invasive strands. The limitations that occurred, sometimes the computer and software are not compatible with each other, because software uses both Python and XML simultaneously. XML allows us to change the parameters that we need to in order to achieve the strands or the size of spheroid, and Python allows us to do it in real time without rewriting the code from scratch. However, new Python version, along with the new, let's say, MacBooks, conflict on some level, so the program crashed on MacBooks like in 90% of the time. However, we were able to do spheroids on PCs and in Mac too. So for the conclusion, cancer spheroids are most valuable for the role that they play in cancer research. Cancer spheroids are important in doing cancer research, drug testing, and development biology. Spheroids in lab takes long amount of time to produce and cost more to produce, so our team has made a digital cancer spheroid. Our goal was to shorten the amount of time spent preparing the spheroids and to make it cost efficient. It's free to use. It has the potential to benefit those researching cancer and tumor growth in labs, pharmaceutical companies, testing cancer treatments, universities trying to teach students about cancer spheroids, and computational models, and anyone else who may need to model tumor. Thank you very much, guys, for your time. Enjoy your day.